Hello science fans, welcome back to Science Fun with Austin. Today we're going to take a look at the other two LAPCA sensors that we didn't get to last time, the electromagnetic field sensor and the ionizing radiation sensor. Let's see how they work. Okay, you can see we have the EMF sensor connected, and the cool thing about this is that it has a low frequency range up to 500 kilohertz and a high frequency range which goes up to 3000 megahertz. So we should be able to differentiate between the EMF emitted from the motors in the microwave and any leaking microwaves. So let's start off with a low frequency here. Calibrating. Alright, so we're stabilized right now around 0.2 microteslas. Let's kick on the microwave and see what happens. Okay, you can see that we got a reading of around 0.8. So we move around them farther away from the motor, we see the reading drop. We go along to the side, you can see the reading go up. Okay, now we'll take a look with the high frequency and see if a lot of microwave radiation is leaking out. Okay, looks like we're calibrated. And we can definitely tell that the microwave has started. There's not a lot of microwave radiation leaking out the side. There is a little bit getting through the front. I think this is definitely low enough not to cause a problem, but it is detectable. For kind of a fun experiment, we'll compare a couple of different types of fluorescent lighting. This is a tube, basically regular fluorescent lighting, and you see we get about 0.27 microteslas here. Let's compare that to a compact fluorescent bulb. Okay, now we'll try a CFL. And you see as we approach the CFL, the levels spike really quickly. Even a decent distance away, we still have a noticeable reading. So you can tell that the CFL electronics are quite a bit noisier than the regular fluorescent light. Alright, and we can get back to sensor oh gosh darn it, it changed my background to Vladimir Putin again. Hold on. Okay, now we have our last LAPCA sensor. This one here detects ionizing radiation. Right now we have it calibrated to read in microsieverts per hour. Of course, the app does ask permission to send data to LAPCA servers, which are presumably in Russia. And you do have to wonder why Russia would want to know if America happened to be radioactive. But let's take a look and see what the sensor actually does. Here we have the americium source that we used to test our tin can radiation detector. Let's see if the LAPCA performs a little bit better. Alright, you can see that it takes a little while to pick up radiation, but we've got the readings gone up from 0.1 microsieverts per hour to about 0.2. So presumably this would be able to indicate whether or not your environment was radioactive. It costs a little bit more than the tin can, but it's a little bit easier to use and you get a cool graph out of the deal. Okay. We've let the radiation sensor run the recommended 2 minutes, and the reading ends up being about 0.46. The background was somewhere between 0.08 and 0.1. So even right next to the radiation source, we're about 4.5 times what the naturally occurring background would be. So you probably shouldn't wear that as an earring or anything, but it's in all likelihood not particularly dangerous. So as a test of our storage procedure, we have the source wrapped in tin foil, and you see we're down to a fairly low reading. So in all likelihood the tin foil is pretty effective at blocking the source radiation, which makes sense because americium is an alpha emitter, and alpha has really low penetrating power. Well, we've tried all 4 sensors that came in the LAPCA Pro package, and they all more or less seem to do what they're supposed to. And the Lapka apps are actually pretty easy to use. So it is kind of a cool data acquisition sensor package. There's the weird thing about it sending radiation data to possibly Russian servers, but besides that, we'd have to give the Lapka Pro the thumbs up. So until next time, have fun, science fans.